We're surrounded by tech that can see. Our phones, our cars, even those massive telescopes peering into the farthest reaches of space. But have you ever stopped to think about how these machines actually turn light into information? Well, that's what we're diving into today, the incredible science of photodetectors.
I mean, really think about it for a second. You point your phone, you tap a button, and poof, a perfect image appears. It feels like total magic, right? But it's not. It's this incredible combination of physics and engineering all happening on a chip that's smaller than your fingernail.
So at the very heart of every digital camera, every light meter, every single fiber optic network is a device that looks something like this. This is a photodetector, and its one job is to do something extraordinary: to catch light and then turn it into an electrical signal that we can actually measure and use.
Now, to really get how these things work, we have to start with the core challenge. Take a look at this number. That is the amount of energy in one single particle of light, a photon. It's a ridiculously, almost unimaginably tiny amount of energy. So the biggest question is, how on earth do you build something sensitive enough to even notice something so incredibly faint?
Yeah, imagine trying to catch one specific raindrop in the middle of a thunderstorm. That's pretty much the scale of the problem engineers are up against. A beam of light is just this torrent of photons, and our detector needs to somehow count them, or at least measure their combined energy. So how in the world is it done?
Well, the answer starts with this amazing phenomenon that was discovered over 100 years ago. It was a complete game changer, a real spark of insight called the photoelectric effect. And this is the fundamental key to turning light directly into electricity.
Okay, so check this out. On the left, you've got an old-school gold leaf electroscope. Early physicists noticed something weird. If you gave it a static charge, the two little leaves would float apart. But if you then shine ultraviolet light on it, the charge would just vanish, and the leaves would fall. Why? Because the light was literally knocking electrons right off the metal. And that exact same principle is what powers the super high-tech detectors you see on the right.
This brings us to one of the first, and still one of the most sensitive types of detectors ever made, the photomultiplier tube, or PMT for short. And the way it works is just brilliant. A single photon of light flies in and smacks into a special surface called a photocathode. And bam! The energy from that one tiny photon kicks out one single electron. But here's the thing. One electron is still way too small to measure reliably. So the PMT does something incredibly clever. It uses electric fields to grab that single electron and accelerate it, smashing it into a plate called a dynode. That impact knocks out several more electrons. And then those electrons get smashed into the next dynode, and on it goes. It's a chain reaction, a total avalanche. By the time it's all done, one single photon has been amplified into a measurable flood of millions of electrons.
Now, photomultiplier tubes are amazing, but let's be real, they're also big, they're fragile, and they need a ton of power. For all the devices we carry around in our pockets, we need something way smaller and tougher. And this brings us to the absolute workhorse of modern electronics, the semiconductor detector.
So what even is a semiconductor? Well, think of a regular conductor like a copper wire. It's got this sea of electrons that are just free to flow wherever. That's your electrical current. But in a semiconductor, like silicon, the electrons are held a bit more tightly. When a little bit of energy knocks one loose, it leaves behind a little empty spot, which we call a hole. This gives us an electron-hole pair. And you can almost think of the hole like a bubble in a glass of water. As the bubble moves up, the water is actually moving down to fill its place. It's this ability to create and move these pairs that is the whole key.
And a photodiode is really just a cleverly designed piece of semiconductor. When a photon with enough energy comes in and hits it, it creates one of these electron hole pairs. Then, a built-in electric field immediately pulls the electron and the hole apart, forcing them to move in opposite directions. And that movement? That's a tiny, measurable electrical current. It's so elegant. One photon in, one electron hole pair out.
Okay, but this is where things get really interesting. Let's set up a little thought experiment. Imagine we have 4 light sources. They're all putting out the exact same amount of power. Let's say 1 watt. The only thing that's different is their color or their wavelength, if you want to be technical. What do you think our photodiode is going to see?
You'd probably expect it to measure the same thing for all 4, right? But it won't. Not even close. And that's because no photodetector is perfect. They all have a kind of bias. This graph here is called the spectral response curve, and it basically shows us that this detector has favorite colors. It's much more sensitive to some wavelengths than others. For this silicon photodiode, it's really good at seeing near-infrared light, but its sensitivity drops off for blue and deep red light.
And so, here's the surprising result. We put the same amount of power in, but we get 4 totally different readings out. This is a huge deal, and it's exactly why for any serious scientific work, you can't just trust the raw signal from a detector. You have to calibrate it, creating a special correction map that accounts for its unique color bias.
Okay, so far we've just been talking about a single detector measuring one little spot of light. But your phone's camera is capturing millions of points all at once. So how do we make the jump from a single pixel to a full-blown picture?
Well, the concept is actually beautifully simple. An image sensor, whether it's a CCD or a CMOS chip like in your phone, is really just a giant grid, a two-dimensional array of millions and millions of microscopic photodiodes all packed together. Each one of those tiny little squares on this chip is its own independent light detector, a single pixel.
All right, now get ready for a fact that might just blow your mind. Those millions of photodiodes on the sensor, they're completely colorblind. Seriously, all they can do is measure the intensity of the light hitting them, not what color it is. They just count up how many photons hit them, and they don't care one bit if those photons are red, green, or blue.
So if you could take a picture with a totally bare sensor, this is what you'd get. It's not a color photo. It's just a grayscale image. It's a map of the brightness values that each of those millions of pixels recorded, which leads to the obvious question. How do we get color?
The solution is absolutely ingenious. We place a microscopic mosaic of color filters directly over the entire sensor array. This pattern is called a Bayer filter. Each tiny pixel gets covered by either a red, a green, or a blue filter, so now each pixel is only allowed to see one specific color. And you might notice there are twice as many green pixels as red or blue. That's on purpose. It's designed to mimic the way the human eye is most sensitive to green light.
The very last step all happens in software. Your camera's processor looks at this sparse grid of color data. For any given pixel, it knows its own color value. Let's say it's a red one, but then it makes an intelligent guess about the missing green and blue values by looking at the data from its immediate neighbors. This process is called interpolation, and it's what fills in all the gaps to reconstruct that beautiful full-color image that you end up seeing.
Now, this whole process of detecting light and using filters to see color might sound incredibly high-tech, but it turns out nature beat us to it by a few 100 million years.
Yeah, your retina is absolutely packed with two kinds of biological photodetectors. You've got rods, which are for seeing in low light, and you've got cones for color vision. But unlike a silicon chip that uses the photoelectric effect, these cells use a photochemical process. When a photon hits a special molecule inside the cell, it actually causes the molecule to change its shape, and that change is what triggers a nerve impulse to your brain.
And what's so amazing is that our eyes get to color using the exact same principle as our camera sensors. We have 3 different types of cone cells. And just like that silicon photodiode we saw earlier, each type has its own unique spectral response curve. We have S cones for short wavelengths or blue light, M cones for green, and L cones for red. Your brain takes the different signal strengths from these 3 channels and combines them to create every single color you have ever seen.
So you see, whether we're talking about a massive photomultiplier tube, a tiny CMOS sensor in your phone, or even the human eye, the fundamental principles are all remarkably similar. At the end of the day, it all comes down to a series of critical trade-offs an engineer has to consider. How fast does it need to be? How much background noise can we tolerate? What specific colors does it need to see? And of course, how much does it cost? And how efficiently can it turn photons into a usable signal?
From capturing photos of your family to detecting gravitational waves from colliding black holes billions of light years away, these incredible devices are literally our eyes on the universe. They translate the fundamental language of light into the data that powers our modern world. And that just leaves us with one final exciting question. What will they help us see next?